Today we're going to be looking at water availability and use. This is how the water moves through the environment and how much we can actually use and why managing it is so important and why it's becoming more urgent. Water may seem abundant, but the amount of availability for human use is surprisingly small. And there's more and more pressure building up to get access to clean water. And this is affected by things like population growth and climate change. For this chapter, we're going to focus on four major areas. First, the water cycle and how that determines freshwater availability. Second, the difference between groundwater, aquifer, and surface water, and why those differences matter for sustainability. Third, we'll discuss water pollution, specifically point versus non-point sources, since these are the ones that influence how we manage water. And finally, we look at major water use laws, including the Safe Drinking Water Act and Clean Water Act, to understand how policy shapes access to safe drinking water. The water cycle is a continuous process, and it keeps water moving throughout the environment, making life possible. Each step plays a specific role in how water is stored, transported, and reused. We can really start anywhere on this cycle, but for simplicity, we're going to start with evaporation. Water from oceans, lakes, and rivers, and even puddles can absorb heat from the sun, and that turns that liquid water into water vapor. And that will rise up into the atmosphere and turn into clouds. The way it turns into clouds is called condensation. This is when that warm water vapor, as it rises up, it starts to cool. And this cooling causes the vapor to condense into tiny little droplets that cluster together. These form those clouds and fog. This transforms the water vapor back into a liquid form. When those cloud droplets grow large enough and heavy, they begin to fall down to earth as rain, snow, sleet, or hail. This step is called precipitation. This is when the water from the atmosphere returns back to the lands in the oceans. Now, some of that water is going to hit the land, and it's going to soak up into soil and porous rock or infiltrate the land, which is why the step is called infiltration. This infiltrated water can travel downward to recharge aquifers, which are underground storage areas that supply wells and springs. Water that doesn't soak in moves across the land's surface. This is known as runoff. It flows downhill into streams, rivers, lakes, and eventually the ocean. Runoff is especially strong when soil is already saturated or rainfall is really intense. Finally, we have transpiration. Plants pull water from the soil into their roots, and they release some of this water into the air through tiny leaf openings. Together, evaporation and transpiration are sometimes called evapotranspiration. Even though Earth appears to be a water planet, almost all of that water, about 97.5%, is saltwater and not usable for drinking, agriculture, or most human needs without expensive desalination. Only about 2.5% of Earth's water is freshwater, and the majority of that is frozen in glaciers and ice caps. That means less than 1% of all the fresh water is actually available in lakes, rivers, and groundwater. In practical terms, the entire global population depends on a very small fraction of Earth's total water supply. As populations grow and climate change affects when and where rain and snow fall, our already limited freshwater supply becomes even more stressed. These challenges are especially serious in places that depend on seasonal snowfall or use groundwater faster than it can naturally refill. Water comes from two main sources. Groundwater is stored in aquifers beneath the soil and rock, and surface water is found in lakes, rivers, and streams. Surface water is easy to access, but can be much more vulnerable to contamination. Groundwater tends to be cleaner, but aquifers recharge very slowly. And over time, overpumping can cause serious problems. Withdrawal too much water and the land can actually sink, causing what's called subsidence. We typically think of this as sinkholes. In coastal areas, overuse can pull salt water into those freshwater aquifers, contaminating the entire drinking water supply. Sustainable water management means balancing those withdrawals with natural recharge rates. Aquifers come in two main types: confined and unconfined. Confined aquifers sit between impermeable layers of clay and rock. This creates a pressure that can cause water to rise on its own when it's tapped, and sometimes we call these artesian wells. Because confined aquifers are deeper and sealed off, they're less prone to surface pollution, but they do recharge much slower than those unconfined ones. Unconfined aquifers sit closer to the surface with a permeable layer above them. They recharge quickly from rainfall, but they're also more vulnerable to pollution because they are closer to the surface where those pollutants tend to be present. These pollutants can include fertilizer, chemicals, or any spills like oil spills. Understanding these differences can help explain why some regions face chronic water shortages or contamination issues while others don't. If we look at this image, we see that confined water layer below. So that confined aquifer is much deeper. And because of that, there's more pressure, and that's what pushes that water up. The unconfined water layer is closer to the surface, and we could see in this image there's a little well that it kind of looks like they're just dunking the bucket down there, like you see in old time movies. But obviously, this one is going to be much closer to that surface, so that pollution is going to get into there much easier, especially if it's open like this. Those little old time wells, lots and lots of pollutants can get into there. When we talk about water pollution, it's important to distinguish between point sources and non-point sources. Point sources come from a single identifiable place, like a pipe from a factory or wastewater treatment plant. These are easier to regulate because you can pinpoint the origin. In contrast, non-point pollution comes from many different sources: agricultural runoff carrying fertilizer and pesticides, stormwater washing oil and trash on the street, or sediments eroding from the landscape. Non-point sources are increasingly the biggest contributor to water pollution, and because they're widespread, they're much harder to manage. Now we're going to take a look at some history of regulations in the United States. Starting in the 1960s and early 70s, the United States was facing growing environmental crisis. Rivers were catching on fire from chemical waste. Untreated sewage was flowing into waterways. Toxic dumping and major oil spills were occurring. These events pushed the public and lawmakers to strengthen water protections. So in 1972, the Marine Protection, Research, and Sanctuaries Act began limiting ocean dumping and creating a way to protect important marine areas after years of unregulated disposal at sea. The Safe Drinking Water Act of 1974 followed growing concerns about contaminants in public water supplies and set nationwide standards for drinking water safety, giving the EPA the authority to regulate pollutants. In 1976, the Resource Conservation and Recovery Act was passed to address unsafe hazardous waste disposal, which was threatening groundwater in many communities. 2 years later, the Clean Water Act expanded protection for rivers, lakes, wetlands, and streams, regulating how much pollution could be discharged and helping cities upgrade their waste management treatment facilities. In 1980, the Comprehensive Environmental Response Compensation and Liability Act was passed. This is a superfund that targeted contamination sites, many of which threatened water supplies. After the Exxon Valdez spill, the Oil Pollution Act of 1990 increased spill response capacity. Finally, the Beach Act of 2000 required coastal states to monitor beach water quality and warn the public of health risks. So, understanding these laws helps us see how environmental policies are supposed to respond to disasters and protect public health.